Hey there, geometry. We are in Unit 5, Lesson 3. There's some hands-on things with this lesson too, which are really hard to do. And actually, last time I taught this lesson live, face-to-face, it didn't go well, so it's okay. I'm still cleaning up Play-Doh from last lesson. So let's talk about creating cross-sections by dilating. You remember dilation from an earlier unit where we had similar figures, and we know they're similar because all the angles are congruent, but the sides are proportional, okay? So if we talk through this, like let's dilate triangle BCD using center P and a scale factor of 2. We would do this using our compasses or straight edges just by measuring. Can't really do that here, but I can say that, okay, if my center is P and I'm dilating by a factor of 2, that means the distance from P to B is going to be the same as B to, that looks about right, B prime. Okay, the distance from P to C is about equal, right there, C prime. And then P to D, D to D prime. So we just dilated it, which is pretty cool. So look at your drawing. What do you notice? What do you wonder? Okay, I have similar triangles. Let's say BC over B prime C prime is going to be equal to BD over B prime D prime, scale factor, right? That's our scale factor. Or we used to use the letter K for it. And I can do that third one too. Sorry, I did BC. I didn't do CD. Is equal to CD over C prime D prime. Okay? If I made all of those sides solid, I would have a triangular pyramid, which is pretty cool. It looks as though these are all parallel, which they are. What else? Angles are congruent. We have similar triangles because we know that angle B is congruent to angle B prime. Angle C is congruent to angle C prime. Angle D is congruent to angle D prime. And we know that from the parallel lines, like this and this, they're corresponding angles, so they're congruent. Corresponding angles, congruent, etc. I think that's it. I'm going to double check though. A really good one. I just looked at the teacher manual to make sure I didn't miss anything. And a good notice and wonder is, I wonder if the area of triangle, not A, BCD, how it compares to the area of triangle B prime, C prime, D prime. I wonder. Yeah, I think that was it. All right. Okay. I guess another thing, like if I did the same thing with a circle and I dilated it, that shouldn't be solid. Like if that was point P, the same thing, same process. Okay, that's a terrible circle. Even if I did a square or a rectangle, okay, it's all the same process. And I can dilate it bigger or smaller, it doesn't matter. The same thing works where we have similar figures, the scale factor, proportional sides, etc. Okay, so a pyramid mobile, this is the one that I've tried face to face. And it's very difficult to do. If we're face to face for this lesson, we will definitely try it again. But basically, if we have sheets of paper, if I look at it from here, if you think about a mobile that you may have had when you were an infant, if you have little brothers or sisters. You have a little hook that you can hang something from, and it's centered. And then you have scaled down, right, shapes that would look like that. So each layer is a scale factor of the layer before it or after it. Such that if you drew a line from here down, it would show you a very symmetrical figure. So here our example is if we had triangles and we did a scale factor of each triangle and it got smaller, 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 and then we stacked them on top of each other, we would make a mobile or a square or a circle or a rectangle or anything else. So what we tried in the classroom was I gave everybody paper, and each student in the group took one sheet of paper and completed the following steps. First, locating and marking the center of your paper by drawing diagonals or another method. If you look at the square, if you just draw two diagonals, they're all going to be equal, and that's going to be the true center. But that's what we did here. I drew on the wrong one. Okay, so we found the true center by drawing diagonals. On the triangle, it's not quite as easy. We have methods to finding the center of a triangle, which we talked about during the triangle unit. Then each student should choose one scale factor from the table. On your paper, draw a dilation of the entire sheet of paper using the center you marked as the center of dilation. So here, somebody picked the scale factor. It looks to be about 1/2 of the blue one, so we're about a half smaller. We could do a scale factor of 3/4. We could do a scale factor of 1/4, and then we would have 4 sheets of paper that would look like that. 1, 2, 3, 4. Oh, I have 5 here. You can keep going, but in essence, you're building a mobile. Measure the length and width of your dilated rectangle and calculate its area. Record the data in the table. This one we're going to talk about because we want to talk about how area works with scaled figures. Okay, that's the important part of this lesson right here. And then cut out your dilated rectangle or square or triangle, whatever it is, and make a small hole in the center. All right, so if we have our scale factors, and this is the ones we talked about, like this is my original. Scale factor of 3/4 just gets a little smaller. This is half as small and even smaller. Then we can do the width and the length and what the area is going to be. So 1 second. So here we have some data to have fun with. I needed my calculator. A sample, these are all squares, and what they did was they used the scale factor and found the length of the scaled rectangle. So the original one is 28 centimeters. And if I take 28 and I multiply by 0.75, I get 21. Okay? So I multiply by the scale factor and I get 21, right? And here, if I take 28 and I multiply by 0.5, I get 14. Okay? They've measured, so it's a little off because we're measuring by hand, right? And if I take 28 and I multiply by 0.25, I get 7, where they got 6.7, because again, human hands make errors. Then if you take, so they did the same thing here. The original one is 21.5, and then they've got all the scaled ones down. And now the area is going to be length times width. So 28 times 21.5 gives you 602. And then 21 times 16 gives you 336, okay? Now what do we do with that? All right, this is, like I said, this area part is the important part. Let me get back to some paper I can write on. So if you guys could write these in, just using the data they got. Because I want to be able to talk about it at another point. Basically, if I take an area of 602 and I want to figure out the scale factor, factor, 0.25. If I do 602 times 0.25, you'd think that I might be able to get that area. I got 150 though. Okay, why is that? Well, we're not just taking the scale factor of the area, we're actually taking the scale factor of the length and the width. So I'm really taking that scale factor twice. Well, let's do this. I'm doing the scale factor of the length and the width. Let's calculate that again. Pretty close, huh? So when we are talking area, we just don't use the scale factor as it is. We use the scale factor squared. And I think that area is always some dimension squared. It's like something, units, centimeters, whatever, squared. So when I'm doing a scale factor of an original pre-image, and I want to find out what the area is going to be of the image, I need to square it. This gives me 338.625, which is pretty close to that. All right, I think we're going to talk about this again in another lesson. I just wanted to give you a preview now. And we're not going to do this cool down right now. This should not be in here. I'm reading it. Sketch the result if you repeated the paper scaling with a piece of paper that was circular rather than rectangular. We would have a half a sphere, or it's a hemisphere. That's just if we scale down. If we scale down and up, we would get a whole sphere. Okay, circular gives us a sphere. It gets smaller and bigger, and it's a ball. All right, I think that's it. Yeah, good job.